Welcome to the final set of videos with regards to the Hydrogen Thermodynamics Toolbox for UHS. Today, I'm going to talk a bit about molecular simulations using the Monte Carlo method. The main goal here is to perform some simulations to calculate the phase equilibrium. In my previous videos, I talked about Maxwell-Stefan diffusion and the Fick diffusion in binary liquid mixtures or gas mixtures. I discussed some basic equations, and then I moved on to showing you how to calculate these diffusion coefficients using MD simulations. We also discussed about the potential inaccuracies caused by finite size effects, which have to be taken care of before you can compute Fick diffusion coefficients from MD simulations. We picked one thermodynamic state point wherein we chose an equimolar mixture of hydrogen and carbon dioxide at 50 megapascal and 323.15 Kelvin. And I showed you how to use LAMMPS to calculate Fick diffusivity. It is important to remember that LAMMPS on its own cannot do these cross correlations, but one has to download the on-the-fly calculation of transport properties, or the OCTP plugin developed by the engineering thermodynamics group at TU Delft to calculate or enable these cross-correlation calculations. In today's video, I will discuss about how to calculate phase equilibria in a multi-component system using Monte Carlo simulations. As a brief recap, I will first show you a bit about how phase equilibria is characterized in a multi-component system. What are the key requirements to characterize a phase equilibrium? I will also give a basic introduction to the continuous fractional component Gibbs ensemble simulations. I will also give you a demo on how to perform these phase equilibrium simulations with the open source software called BRIC. Again, BRIC is developed by the engineering thermodynamics group here at TU Delft. We pick an example of hydrogen and carbon dioxide and water and perform a simulation using the BRIC software and calculate the vapor liquid equilibria for this particular state point. I have not mentioned it here, but once again, we pick the state point corresponding to 50 megapascal and 323.15 Kelvin. The references for today's talk are, or the contents for today's talk, are borrowed from these papers here. The papers by Hens et al., Polat et al., and Rabari et al. All summarize the key aspects of the CFC-MC, or the continuous fractional component Monte Carlo simulations, and also highlight the key features of the BRIC software and its functionalities. BRIC is available as a free open source software that can be downloaded from the GitLab page maintained by the engineering thermodynamics group. For the basics of Monte Carlo simulations, one can always refer to Frenkel and Schmidt and also Allen and Tildesley. Let us first briefly refresh and reflect on how phase equilibrium is characterized in a multi-component system. Let us assume that we have this box which maintains a constant pressure and temperature. Assume that this particular box here contains a multi-component mixture in the alpha phase and beta phase. For simplicity, you can assume that the alpha phase is a gaseous phase and the beta phase is a liquid phase. Since it's a multi-component mixture, both the alpha and the beta phases will contain all the n components of the system. At phase equilibrium between the alpha phase and the beta phase, the following relations should hold. Firstly, the pressure in the alpha phase should equal the pressure in the beta phase. Similarly, the temperature in the alpha phase should equal the temperature in the beta phase, and that should be equal to T, because that is what you impose here. Similarly, for the pressure, it should be P alpha equal to P beta equal to P. Finally, the most important condition is that the chemical potential of component I, where I can vary from 1 to n, in the alpha phase and the beta phase should be equal at a given pressure and temperature. A system that satisfies all the three conditions for all the n components are said to be in a state of phase equilibrium. If one does not satisfy the equality of chemical potentials for each component, then this would mean that there's a net mass transfer from one phase into the other. And this mass transfer would happen until then there is no more mass flow. Thus, equality of chemical potential is an important condition to satisfy during phase equilibrium. For further examples and further explanation, also refer to Frenkel and Schmidt. I will now briefly describe the continuous fractional component Monte Carlo, or the CFCMC method. In a Monte Carlo method, as I've already told you, we are not interested in the dynamics of the molecules itself, but rather in just the configurations of the molecules that are generated. For Monte Carlo simulations, one can calculate densities, chemical potentials, enthalpies, and so on. In a continuous fractional component Monte Carlo method, a simulation box contains something called as a fractional molecule that is highlighted in the white circle shown here. The fractional molecule can be identified because it has something called as a coupling parameter that varies between 0 and 1. When the coupling parameter lambda equals 0, the fractional molecule has no interactions with its surroundings and it behaves like an ideal gas molecule. When lambda equal to 1, the fractional molecule behaves like a full molecule with full-blown interactions with its surroundings. When I mean interactions, I'm mainly referring to the Lennard-Jones interactions and also the electrostatic interactions that are relevant for this molecule with its surroundings. Now, for an intermediate lambda between 0 and 1, all of these interactions are scaled. The expressions for the scaled Lennard-Jones and electrostatic interactions are available in the brick manual. Now, lambda has a probability distribution. To ensure that sufficient statistics or sufficient advantage is obtained from this CFCMC method, it is important that all values of lambda are equally sampled. It can happen that a molecule can get stuck at a particular value of lambda because of its interactions with its surroundings. When it is stuck at a particular value of lambda, it can mean that the molecule has to overcome a huge energy barrier, which might not be possible. Thus, to ensure a uniform sampling of lambda, one can use something called as the Wang-Landau sampling. I will come back to this point at a later time and tell you how exactly it works. The main advantage of using CFCMC simulations is that it is possible to calculate chemical potentials, fugacities, and many other properties like enthalpies in dense systems. The problem encountered in Monte Carlo simulations, which is just the MC simulations, is that in dense systems, insertion of particles becomes really difficult. Thus, the CFCMC method is powerful in determining the phase equilibria of multi-component systems. Now, I will briefly describe how the Gibbs ensemble Monte Carlo simulation works, which are useful to calculate vapor-liquid equilibria for systems that are of interest to underground hydrogen storage, or for any other systems for that matter. As you all remember, there is a NPT ensemble in which the pressure, temperature, and the number of molecules are fixed. So we use the NPT version of the Gibbs ensemble to determine the VLE, or the vapor-liquid equilibria of multi-component mixtures. When I say vapor-liquid equilibrium, what I'm interested in is to calculate the solubilities, or to calculate the fractions of the different molecules in the vapor and in the liquid phases of a multi-phase, multi-component system. To demonstrate an example, please consider this particular system where you have a small box or two boxes here in which you have the liquid phase and you have the gas phase consisting of CO2, hydrogen, water, and sodium and chloride. In the Gibbs ensemble simulations, you always have two boxes. One box contains the dense phase or the liquid phase, and then the other box contains a gaseous phase, as shown here. As you can see, the dense phase contains mostly water, which is obvious considering that water has a higher density compared to the gaseous phase. And then you have a box with a larger volume, which mainly contains gases. As you can see here, you have CO2 molecules also combined with H2 molecules that fill this box, and with small amount of water molecules that are distributed evenly here. Now, to ensure that an equilibrium is reached such that the final state represents the vapor-liquid equilibrium, we perform some trial moves in this simulation. Trial moves are given by the following. You have a translation of a molecule, you have a rotation of a molecule, you have volume changes, and then you have change in the value of the parameter lambda, and you have molecule transfer trial moves. A description of all of these will follow now, but for further details, one can refer to the BRIC manual and also the references therein for an explanation of Gibbs ensemble. During translation and rotation of a molecule, you first have to consider what happens to the energy of the system when you rotate or translate a molecule. For this, a box is chosen, and for demonstration purposes, I only pick the dense box. What I discuss now is equally valid also for the gas box. Okay, once you choose a box, you randomly pick a molecule within the box and you perform a translation. The translation distance is also specified during the input to the BRICS simulations. Once you perform or execute a translation, the position of the molecule with its surroundings has now changed, which then means that the energy of the system has also changed. The change in the energy due to the translation is given by this term delta U. And delta U is nothing but the energy of box I as a function of this set of coordinates Sn for all the n molecules. N here means nu, the lowercase n means nu, and the uppercase n means the scaled coordinates of all the n molecules, minus the energy U in box I with as a function of the old coordinates, plus a contribution due to the existence of the fractional molecule. Now, if the fractional molecule exists in the same box as in which the translation is executed, then this particular parameter here called the delta function or the Kronecker delta will be 1 because I equal to j equal to 1. Now, if the fractional molecule is in a different box, then this term is not important and can be neglected. And the change in the energy with respect to the fractional molecule is given by this particular equation, where S-frac is the scaled coordinate of the fractional molecule, and n corresponds to the new set of coordinates. And here again, n corresponds to the new coordinates, and nj is the jth molecule, and lambda is the value of the fractional parameter. Now, once the delta U is calculated, it is plugged into this equation. Now consider the case when delta U is less than 0, which means that the energy of the system has decreased after translation from this point to this point. Then the exponential of this function will be a quantity greater than 1. So the minimum of this function will be 1, which means that the acceptance probability of such a move is 1, and this new system state is accepted. As a result, one would execute the translation of this molecule from this point to this point. Now let us assume that delta U was less than zero. Sorry, let us assume that delta U is greater than zero. In the case that delta U is greater than zero, it means that the molecule has moved into a position where the overall energy of the system has increased. This means that this is unfavorable. Then this would be a function, or the exponential of this quantity would be a number less than 1. Now, let us assume, for example, that this quantity simplifies to 0.5. Then what this entire function then tells me is that the new state should be accepted with a probability of 0.5, which means that even with the knowledge that the system is increasing its overall energy, we accept it, but only with a probability of 0.5. If this number here would correspond to a number less than 0.1 or 0.01 and so on, it would mean that the new state will be accepted with a very, very low probability. Thus, the translation of a molecule is accepted using this acceptance rule. A similar argument can be also extended to rotation. Once you rotate the molecule around its position, then its interaction or the distance between the atoms of that molecule with the surrounding atoms of the neighboring molecules also changes, resulting to a change in the overall energy. And once again, you can calculate the delta U's and you can calculate the acceptance rules for such a state. Once again, I repeat that if your fractional molecule does not stay in the same box, then this particular term can be neglected. In the event that the fractional molecule is in the same box as your molecule that is chosen for translation, then this term contributes to the overall change in the energy. The next set of changes are called the volume changes. What essentially happens is that you execute a volume move in which you either increase or decrease the volume of the chosen box. Once again, for the purpose of demonstration, I choose the dense box for this particular case. The acceptance rules, or the acceptance rule for this particular change is given by this expression. I will not derive this expression, and this can be found in the BRIC manual. What is important to notice is that you can see two new terms. You can see VI, where I is the box index, and N means the new volume of box I. VIO means the old volume of box I. Note that you have a term called delta U here, which means that once you change the volume of the box, you're also changing the relative distance between all the volume or all the distances between the molecules, which means that you're also changing the overall energy of the system. And finally, if you scale the volume of the box in which the fractional molecule is present, then this term corresponds to 1. Since we're performing an NPT ensemble Gibbs or the NPT Gibbs ensemble simulations, the pressure is already encoded into the acceptance rule. So you're strictly enforcing the pressure of the system. Once again, similar to what was given before, you have to calculate what the delta U is. As I mentioned, since you're expanding the box, the relative distance between the molecules is also scaled during the change in the volume of the box. As a result, you end up with this expression for delta U. Now, plugging in the new volume and also the delta U due to this change relative distance between the molecules, you can once again calculate the exponential of this entire term here, and you can determine whether you accept or reject the move. The next set of moves are called the changing the configurational parameter or changing the parameter lambda. When you change the value of lambda, you can either increase the value of lambda or decrease the value of lambda. Once again, the acceptance rule is pretty straightforward, where you say you choose the minimum of 1 and the exponential of minus beta delta u. And delta u is the change in the energy in the box where the fractional molecule is located. And as you can imagine, if the fractional molecule, the value of lambda of the fractional molecule is enhanced or increased, then it changes the strength of the interactions with the neighboring molecules, which then changes the overall state or the overall energy of the system. Similarly, decreasing the value of lambda also has an effect on the interaction between the fractional molecule and the neighboring molecules, and thus has an overall effect on the energy of the system. Once again, the value of delta U can be plugged back into the system, into this equation for the acceptance rule, and can be decided whether the move should be accepted or rejected. The next set of moves are called transferring or swapping a fractional group. What happens here is that you choose a particular fractional molecule in box I, and you transport that fractional molecule to box J in a random position. While you're swapping or while you're changing the position of this fractional molecule into a new box, you do not change the value of lambda. So it is strictly changing only the position of the fractional molecule. The acceptance rule for such a move is given by this expression here. Note that you also have a volume or the ratio of the volumes corresponding to this swapping of the fractional molecule. The delta U term is given by this expression, where now the fractional molecule encounters a new environment, and because of it traversing to a new environment, the overall energy also changes. And the difference in the new configuration and the old configuration contributes to delta U. I once again stress that while you're swapping the molecule from box I to box J, the value of lambda is preserved and is not changed. The only additional change is that you have the volume ratio of box J to box I. And the last and the final type of a trial move is called changing the identity of the fractional group. When you're changing the identity of the fractional group, you're doing two things here. Firstly, you're changing the fractional molecule in box I to a complete molecule, which means that the fractional molecule whose value is lambda old, becomes 1. As I have already mentioned before, when you change the value of lambda to 1, it means that it feels like a complete molecule. Correspondingly, what would happen then is to pick a complete molecule in box J and make it a fractional molecule with a value lambda O. Here I have put in the value lambda OI to just stress the fact that the value of lambda equals to the value of the lambda for the fractional molecule in box I. To summarize, so you have two effects here. In box I, you change the fractional molecule to a whole molecule, and in box J, you have a whole molecule which is changed into a fractional molecule whose value is then lambda 0. As a result, you're changing the overall energy of the system, and the overall energy in the system is the overall change in the energy of the system is given by this particular term. Note that you previously had a ratio of the volumes that entered into the into the rule for the acceptance, but now you have the ratio between the particle numbers. As I said, to characterize phase equilibrium, the most important thing is to determine the chemical potential of the ith species. The chemical potential of any component in the liquid and the vapor phase, or in the alpha and the beta phase, should be identical. And if this happens for all the components in the system, then you've truly reached equilibrium. And the expression for the chemical potential of a component is given by this expression here. Note that the key parameter here is the probability of lambda in box I for component I, and that's the ratio of the probabilities at lambda equal to 1 and lambda equal to 0. Now, at phase equilibrium between the alpha and the beta phases, the following relation holds, as I mentioned before. The pressure in the vapor phase and the liquid phase should equal the total pressure. The temperature in the vapor phase and the liquid phase equals the temperature equals to the temperature that we wish. And finally, the chemical potential in the vapor phase equals to the chemical potential of the liquid phase for every component, where I varies from 1 to n. So let's now work out an example on how to simulate the Gibbs ensemble using the Brick software. So what I'm showing you here is the home page of the Git of the Brick software. So it's called Brick CFCMC. Now you should be able to locate this from your web browser as well. Instead of opening it like this, let me just show you how you can search. So you can say Brick CFCMC. And the first link that comes up is the Brick CFCMC by the Engineering Thermodynamics group at TU Delft. All right, the first step to all of this is to clone the Git, clone the repository of the Brick CFCMC from GitLab. So this you can do, and this is not very difficult, but let us do this. You see that all of it works now. Now you can add these following lines to your bash so that it becomes easy for you to access Brick from anywhere. So for me, it is the bash profile. So you see here, I've added the lines here. So this has worked well for me. So you can see that I have the same set of lines. So once you have it in your bash profile, you can then do source bash rc. And if you're using an Apple, then perhaps the right command for you would be source bash profile. Sorry for this, because I have Conda that's activated, so I have to deactivate that. Now you can also compile Brick software, and you can say Brick compile, and here you can create executables, so you can compile with an Intel compiler or with a Fortran compiler, and so on. And you can also compile a version that provides you debugging options. So to save all of the time related to it, I'm just going to compile it using Fortran. So I say brick compile -g, and you will see the following line that shows up. Now, the nice part about all of this is that the manual is extremely well written, and all of the information is available in the Brick CFC MC manual. So here you see how to install it, obtaining Brick, setting it up, compiling, and so on. Also how to update it. Then you also have the options to run and so on. So this is very well written and very instructive, and you do not have to worry that you will miss the intermediate steps. So that's not a problem. Now it says that an executable has been created, and perfect. So note that the Brick GNU Fortran debug is generated, but you also have other executable files in the executables. So this is not my home version of Brick. So let me go to my home version of Brick. And you see that you have the Brick GNU Fortran optimized. So if you want to actually compile it, not the debugged version, but the optimized version, then you say -g -o, and this gives you the version which is optimized for GNU Fortran. As you see, you now have the executable called Brick GNU Fortran optimized, and you can check that it is indeed the one that was generated because of the command that I ran now. So it says May 31st at 2:57, and it is in fact the time right now. Okay, so once the software has been installed, now I have already created the input and the run file, but you can also do this fresh. You can just say brick new as shown here. Brick new, my first simulation. It then creates a new directory. So it can be, or you can even say CFCGE, and then you're inside the folder CFCGE. But I have already created an input folder for you corresponding to the H2CO2 water mixture. So now let us go through what are the various files within the input. Now, the first thing to do is to let Brick know the geometry of the CO2 or the carbon dioxide file. This is very similar to LAMMPS. And in the first line, you mention what is the molar mass in grams per mole, and that is 44.01. You can say that CO2 has 3 atoms, which is oxygen, carbon, and oxygen. And the position of the atom is 1.16 because this is the Trappe force field. Then you need to adopt the um, geometry that is provided in the Trappe database. And I've already shown you the website corresponding to the Trappe database. Now, if you really want me to go through it once again, we can do that. So Trappe CO2. So here you can say CO2. And you have all the parameters here. So you see that the bond length of the Trappe CO2 should be 1.16 angstroms. So this is all provided here. Now you have two bonds between 1 and 2, which means between oxygen and carbon, and then between carbon and oxygen, which is 2 and 3. And you do not have any bending in the CO2 because it's a rigid molecule. There are no torsion angles and there are no intramolecular interactions. Now, similarly, you can do the same for hydrogen, and this is exactly the same methodology that we adopted for initializing hydrogen on LAMMPS. This is the gram per mole or the molecular mass of hydrogen. You have three atoms, the dummy atom corresponding to the Marx force field. Then you have the hydrogen and the hydrogen at the two extreme ends. And you have two bonds, one between hydrogen and the dummy atom, the other between the dummy atom and hydrogen. And there are no bending because this is a rigid molecule. Once again, no torsion and no intramolecular interactions. And finally, you can look at the force field for water. Now, this is called the tip 4p mu, a force field for water, which is once again developed by the engineering thermodynamics group at TU Delft. And the paper corresponding to that was, or can be found here. So this must be the most recent paper with regards to the let us see. Yes, so this should be the paper where you can find the force field for the tip 4p mu. So in this, in the SI of this particular manuscript, you must be able to find the force field parameters. Yep. So here are the force field parameters for water. So this is the modified tip 4p. That's why they've called it this work, but this was later on named to tip 4p mu. And the parameters of these force fields are provided here. Note that you have 4 atoms. So this is a 4-point model for water. You have the oxygen, you have the hydrogen, and then you have the dummy atom called N. You have 3 bonds. So here I'm not discussing in detail the force field for water. If you're interested, you can read the paper here and also read the original TIP 4P 2005. So the modified here means that the original force field TIP 4P 2005 introduced by Abascal and Vega by Reza has been named as TIP 4P mu. Now there are 3 bonds between 1 and 2, that is between oxygen and hydrogen. There's between 1 and 3, again between oxygen and hydrogen, and then between 1 and 4. So the geometry is, and the distances between all of these is specified here. Note that you have to probably do a bit of math to get these angles right and so on, but this is pretty straightforward. And the molecular mass of water is 18.0154. Once again, there's no bending because we are simulating only rigid molecules. There is no torsion, and there are also no intramolecular interactions. Fine. Once we set up all the input files or the different geometries, the next step is to specify the force field. So now you have to describe how the atoms interact with each other. So you have firstly the oxygen from the water. So remember that when you specify the force fields, you have to preserve the notation that you have used for all the atoms. So for example, here in the input file for water, you say oxygen tip, and you have to use the exact same naming convention here. Similarly, if you're using hydrogen tip, then you also specify the hydrogen tip here, because you also have a hydrogen coming from H2. All right. Similarly, you have the M tip and so on. So you have oxygen and carbon for CO2 and the hydrogen and the dummy site for H2. Notice that there is no repetition of oxygen or there's no repetition of hydrogen in the water molecule corresponding to the two hydrogen atoms, because the same rule applies for both of the hydrogen atoms. That also holds for the oxygen in CO2 and also the hydrogen in H2. Now, the main parameters here are the sigma and the epsilon, corresponding to the Lennard-Jones interaction parameters. This is something that we already did in LAMMPS. So this is pretty straightforward. We do the exact same thing. The key thing to notice here is that the epsilon is not in terms of kilocalories per mole, but it is in units of, epsilon over kb. Yeah, which means that it is in units of Kelvin. So that is the only difference between here and in LAMMPS. Now we specify that this is purely a Lennard-Jones site, and it does not participate in electrostatic interactions. And we say that this should be printed as OH in all the output files that Brick produces. Now, similarly for hydrogen tip, we see that it is not a Lennard-Jones site, and you can also recognize that by the 0 and 0 in the sigmas and the epsilons. It has a partial charge corresponding to 0.53136 and so on. Now you have to specify that it's not a Lennard-Jones site, but even if you say true for the Lennard-Jones site, you would end up with all zeros. So it wouldn't matter. And finally, you have the electrostatic, which is true. So the hydrogen in the water molecule participates in the electrostatic interactions. And I print it as H. Now you can do the same for all the other species in this particular molecule, or for the water molecule, you do the exact same thing for the oxygen and the CO2. You also do the carbon in CO2. Now, kindly be reminded that the sigma and the epsilon is to prescribe interactions between the carbon in CO2 with another carbon in CO2. Similarly, oxygen of CO2 reacting with another oxygen in CO2 has the following Lennard-Jones parameters and also electrostatic parameters. Notice also that all the charges are such that the system is neutral or charge neutral on the overall, because 0.53136 times 2 should give you 1.06272, which is then nullified by this minus 1.06272. Similarly, for hydrogen, also is charge neutral, and we adopt the same technique as what we did for specifying the hydrogen in LAMMPS. All right, so we have now described all the atoms that participate in this calculations. The total bending types are 0 because we do not have bending in any of the molecules. These are all rigid molecules. Similarly, there are no torsions, so there are all 0 torsions. Finally, now we describe the cutoff, interaction cutoffs in this file, similar to LAMMPS. Once again, the ideal gas contributions are off, we say false. cutoff for the Lennard-Jones interactions are 10 angstroms. So that is the same for both the box. And I strongly suggest, or I strongly recommend, that the cutoff for the Lennard-Jones always be the same for both the box 1 and box 2. Here, by designation, I assume that box 1 is the dense box and box 2 is the gaseous box. Now, for the electrostatic energy, we use the Ewald summation, similar to the PPPM method in LAMMPS. When the cutoff energy for, or the cutoff interactions, or the cutoff length for the electrostatic interactions in box 1 is 10 angstroms, but box 2, we keep the electrostatic interactions to a length of 23 angstroms. Now, the reason for such a large value of the electrostatic cutoff is that the gaseous boxes are huge boxes, which means that you need larger interaction lengths. But the important thing to notice here is that in the calculation of electrostatic energies, we are interested in the relative precision. And by choosing the cutoff, the alpha, and the Kmax with these values here, we ensure that the electrostatic precision in the calculation of the electrostatic energies is of the order of 1 e 6. Now, the way to choose the values of the electrostatic cutoffs is very clearly mentioned in the BRIC manual. So I will show you these equations that are relevant for choosing the electrostatic parameters. So choosing the Ewald parameters is given by this particular set of formulas. So if your box has a length L, then you choose a cutoff equal to 0.4, the length, and then you choose an alpha parameter, which is precisely the alpha electrostatic energy here. And then you have the N max, which is basically the K max here, and so on. And the parameters eta and omega can be calculated using these separate set of equations. Overall, all of the parameters here can be calculated. And when I perform these calculations for my system, then I get these values here. Now, all of the Lennard-Jones interactions are truncated at 10 angstroms, which means that we have to correct for the remaining interactions or the residual interactions, and that is incorporated by using tail corrections. So here the tail corrections have to be included. The mixing rules is Lorentz-Berthelot, which means that if an oxygen if an oxygen interacts from water with an oxygen from carbon dioxide, then you have to consider the Lorentz-Berthelot mixing rules to calculate the interaction parameters of sigma and epsilon for the interaction between oxygen from carbon dioxide and oxygen from water. Because remember, these sigmas and epsilons are only for the interactions between the oxygens in the same molecule. So if I have oxygen from carbon dioxide, then if the oxygen is interacting with another oxygen from carbon dioxide itself, then these are the parameters that you have to use. But if your oxygen from carbon dioxide is reacting with an oxygen from water, then you have to use a mixing rule between the sigma of oxygen and the sigma of carbon dioxide, sigma of the oxygen of carbon dioxide. There are no overrides, which means that all of the interactions can be calculated using the Lorentz-Berthelot mixing rules. If in any chance there are certain overrides or certain exceptions to the Lorentz-Berthelot, then these can be mentioned here in the overrides. So once you have specified the force field, you can then specify the topology. Now, in the topology, we now specify how many molecules of each of these components should be in either of the boxes. For simplicity, I start, as I said, I initialize box 1 as the dense phase box, and there are 400 molecules of water, and the gaseous phase consists of CO2 and H2. And I decide to put in 100 molecules of CO2 and 100 molecules of H2. Now, remember that this number can be increased as much as possible. There's no issue with that, but also be warned that the simulations become extremely slow because you have to consider that you have Lennard-Jones interactions and also the electrostatic interactions, which are expensive to calculate. And with more the number of molecules, your Monte Carlo simulations also become very, very slow. Now, we have to specify the fractional molecules. Now, we specify that it's a Gibbs ensemble simulation, the type. Then we initialize all of our fractional molecules in box 1, but this is purely a choice. You can do it in either of the boxes. Now, you can also choose how many molecules are present in a fractional group, and we say that a fractional group, in this case, should only contain a single molecule. And in the first fractional group, I have one H2O molecule. In the second fractional group, I have a CO2 molecule. And in the third fractional group, I have a H2 molecule. And I specify them, or I call them by the name H2O tip, CO2 frac, and H2 frac. You can also say H2O tip frac for the sake of consistency. Notice that I'm not considering any reactions here, so that can be switched off for now. Now here I specify the box length. Now box 1 I say should be 25 angstroms. So the 400 molecules that I choose here for water should be packed within a box of size 25 angstroms or with a box length of 25 angstroms. Now I have already mentioned that you can change the volume of the box in one of the trial moves, or you move the or translate the molecules. But you also need to specify what is the change in the volume and what is the change in the translation, or what is the change in the displacement of the molecule. Of course, you cannot give extremely high values or very low values because these are then will not lead to the right sampling. So the nice part or the very powerful feature of Brick is that you can start with a very random value. Let's say here D volume is 125. Now, what is important to note is that the Brick software automatically adjusts the D volume and also the translation distances and so on, such that the overall probability of acceptance is roughly around 50%. And the reason why this value of 50% is chosen is because it allows you to sample both accepted states and non-accepted states, and it helps you to arrive at the right statistics. Now for box 2, I choose a box length of 56.4. I choose a bigger box length because it's a gaseous phase, so it has to be more expansive. Now, a quick estimate for the box length can be obtained by calculating the densities at the chosen pressure and temperature, and then back calculating what should be the size of the box such that you end up with the same density that you're interested in at a given pressure and temperature. So finally, you also then specify what should be the maximum translation and what is the maximum rotation in either of the boxes. So notice that the water can translate by a maximum of 0.62 of the size of the box. CO2 can also translate by a maximum of 0.62 by the size of the box. So 0.62 is the fraction of the entire box that it can translate. And the rotation is 90 degrees. That's the maximum rotation that you can provide a molecule in box 1. In box 2, you see that the maximum translation is 10. And the reason for giving such large translation distances is because it's a dilute phase, which means that you have more vacant spaces in the simulation box, which you can then translate. Similarly for CO2 and H2, and also here the rotation is 90 degrees. Like I said, the values for these which you prescribe will be overridden after the initial phase of the simulation, such that the simulation can ensure a 50% acceptance rate. So these are just the starting values. Now we also have to specify what is the maximum d lambda for each of the fractional groups. So here we see in box 1 the fractional d or the fractional lambda can change by a maximum of 0.4, 0.4, and 0.4 for each of the three components, that is H2O, CO2, and H2. Now notice that it's the same for both the boxes, and unlike the translation or the maximum translation and maximum rotation, the maximum d lambda does not change in the course of your simulation. So remember that we have P of lambda, which is the probability for a molecule to have a particular value of lambda. And to determine the probability at multiple values of lambda, you need to then have lambda bins. So here I segregate it into 100 bins, which means lambda has 100 values that it can take between 0 and 1. Or lambda can take continuous values, but for the sake of discretization, we have 100 bins. Now, notice that there's a particular value here given by lambda switch. What we say here by lambda switch is to notify when your lambda can take on a particular value. So let me show you exactly. Your lambda switch basically corresponds to this particular here. So what it means is that the Lennard-Jones interactions become completely developed after a value of 0.6. And here also the electrostatic interactions start to develop from the value of 0.6. So that's precisely the value of lambda, and this can be chosen based on your particular problem, but as a default, I've chosen 0.6 here. Now, finally, we will see the settings that we require to run this simulation. So here I specified that we should have two boxes. Sorry for this. So I specify here that we have two boxes. The temperature should be 323.15 Kelvin. The pressure is 50 bar, and the let me see. So here it's asking me whether I want to provide everything in reduced units, which means that I specify things that are normalized by certain parameters, but here I say that should be false. Now I have to choose the number of cycles. So in MD, we always had the number of time steps for a simulation, and here we have cycles. So in MC simulations, I have chosen that we have initialization cycles, which is equal to 1E4, which means that in the initialization cycles, all of the translations and rotations are performed, and also all the overlaps are removed such that the system comes down to a minimum energy configuration. And then we specify something called as the equilibration cycle. And during the equilibration cycles, the probability of lambda is built up, or the weight function is built up, and it roughly takes around 1.5 E6 cycles. So that's the number of cycles in which we allow the system to build a weight function. Now, this value is small. I mean, this value can be changed. You can make it as large as you wish, or you can make it as big as you want. But the issue is then that your simulations become extremely low. So a good test or a good idea is to always start with a low number and check if the weight function in your simulations has sufficiently converged. And the way to check this is to see how smooth your weight function is, because you have a lambda bin, and the weight function is a function of lambda, and this has to be more or less pretty smooth. Now, to show you how a weight function looks, this is the paper by Pursaid Isfahani or Pursaid Isfahani and co-workers, where they use the Gibbs ensemble in the CFC-FC method, and they calculate the weight functions for a system consisting of um, Lennard-Jones particles at a reduced temperature of 0.8. And you see that the weight function here is pretty smooth, and you have a weight function that looks like this. Now, they have the gas phase and the liquid phase, and you see that the weight function is pretty smooth for the liquid as well as the gas phase. Now, the weight function is in units of kBt, which means that you have huge energy barriers corresponding to the liquid system. So the weight function for the liquid is pretty smooth, and you see also that the weight function is steep, and it also corresponds to close to a 6 kT, which means that the liquid phase or the insertion in the liquid phase is quite energy expensive. All right, so in the equilibration cycle, as I said, you end up building the weight functions, and finally in the production phase, you use the weight functions to run the simulations. Okay, so now here are some of the output parameters. So you can print the radial distribution function, which I choose to be 0 right now. You can also produce averaged quantities. So you can average the volume, the number of molecules, and so on. So a detailed explanation of this is available in BricsCFCMC manual, where all of the parameters are explained in detail. For example, you can see what it corresponds to. So N average is the number of cycles after which averages are updated in any simulation. And then these will ultimately be outputted. The N data is the number of cycles after which averages are written to a file, which means that here, when I've chosen 100 and 100, it's going to average every 100 cycles, and then it's going to output the data every 100 cycles. N configuration is the number of cycles after which the configuration, that is the position of the molecules and the atoms, are returned to the output. And this is only during the initializing and the production cycles, and not during the equilibration cycles. Here, init is set to true, which means that I start with a random configuration, but it is also possible to start with an initial configuration that is that can be read from a file. So, for example, if you say false, you need to provide a restart.in file in the input. Now, you can also start with a weight function instead of building the weight function from scratch. And if you have to build a weight function, then you say true, but then you have to generate the weight function, or you need to supply the weight function.in for the simulation. And this can be done by feeding in the weight function that you ran from a previous simulation and feeding it as the starting point. Because be warned that sometimes building a weight function, an accurate weight function, can take quite a bit of time. So it always saves you some time if you start with the weight function that's already available. Now, you can provide a seed to the function for the sake of reproducibility. So if you want to if you want to debug your simulation and so on, you can use a seed, and you can also provide seeds so that you start with a different starting point each time. And here is a value of seed that is chosen. So here I've said seed is equal to false. So it generates a seed automatically in the program. Now, all of these are currently of not not of interest to us, so I will not be explaining this for now. But these are basically the radial distribution functions with respect to the molecule, and these are the radial distribution functions with respect to the atom. We do not perform any insertions, and these insertions meaning these are Widom insertions. But as of now, I will not get into the details as we are not using this. Finally, in this, we use something called as the Wang-Landau sampling, or the Wang-Landau scheme. And the Wang-Landau scheme is used to construct the weight function. And we say true here. If your weight function is already constructed, then do not use the Wang-Landau scheme to construct the weight function. Now, I've just chosen the default values for the Wang-Landau scheme, and I will not get into the details of this because this you can play with it, and you can find the right values also by looking at the appropriate manuals and also the original article by Wang and Landau. Okay, finally, now you choose the translation moves, the rotation moves, which I discussed. So I choose that 35% of my moves should be translation, 24% of my moves should be rotation, only 1% of my moves should be volume. Notice that the volume moves are very expensive because you have to change the position of all of the molecules. The scaled coordinates of the molecules are to be altered, and the corresponding energies and the forces have to be, the corresponding energies have to be calculated fresh. So that's the reason this is performed with minimal frequency, because then your time consumed for such a move is also less. Now, there are no intramolecular moves because there's no bending. I do 20% of my moves as lambda moves, in which the values of lambda are changed. Then the remaining 20% of my moves is CFC hybrid moves, in which the value of lambda is changed in a box, and like the changes that I show here, where the swapping happens, where you can pick a fractional molecule and place it into another box at a random position, or you change the value of lambda in one box such that it becomes a full molecule, and you change the full molecule in another box to a fractional molecule with the same lambda. So this is pretty much what the hybrid move means. And here in the hybrid move switches, we say this should be 0.3 and 0.7. What this means is that your swapping is usually performed for lambda values of fractional molecules that are less than 0.3, and you only do the change in the identity of the fractional group once your fractional molecule has changed to more than 0.7. So these moves are only executed for lambda less than 0.3, and then the identity of the fractional group is changed only if the lambda is greater than 0.7. So these are basically the switches. And all of the descriptions are also provided here if you wish to have a look. Now, this is pretty much it. I have explained all of the input parameters. And finally, now we can run the simulation. All you have to do is say run and sim.log. and see that the simulation has already started. Now, it's important to note that it is that the sim.log file always tells you whether the simulation is running or whether it has abruptly ended. So it is good to check this simulation.log from time to time to ensure that your simulation is progressing as planned. All right. Now in your output file, you can basically see a list of files that are outputted. So you can see that there's a volume versus cycle.dat, there's a number of molecules versus cycle.dat, and so on. Now, since the simulation is running and it will take time, I will show you in an alternate simulation how each of these parameters look. So here you can see how this output file looks. So you see that at cycle number 100, you have 394 molecules of water, 6 molecules of CO2, 1 molecule of hydrogen. And similarly in box 2, you have 6 molecules of water, 394 molecules of hydrogen, and 399 molecules of CO2. So this is for one particular case where I've chosen actually 400 molecules each of water, CO2, and H2. But in principle, this is more or less how your output file will look like. So you can also see at the latest how it looks. So this is also the volume versus cycle. So it tells you what is the volume of each of the box as a function of the cycle number. So you can see that the liquid box has lower volume compared to the gaseous box by almost an order of magnitude. You can also look at the density versus the cycle, where the density of each of the component is inside each box is printed as a function of the cycle. Now, the most important thing is then the weight functions, because that is what you use finally to calculate the chemical potentials. So you have a weight function for each of the species. So you see that you have a weight function that is produced after each cycle. So now if you want to calculate the chemical potentials, you can then use the weight functions in this particular file. So with this, I hope to have shown you how to run a simulation in the CFC Gibbs ensemble. Now, to calculate the solubilities, one can always look at the AV number, the file called the AV number of molecules, or the number of molecules as a function of cycles, and you can plot the average number of molecules for each of the component in each of the simulation box. And with this, you can also calculate the solubility of the you can calculate the respective mole fractions of each of the components, and then you can arrive at the correct solubilities. So this would then tell you, and you can do this at every state point, and with this you can then calculate the entire vapor liquid equilibria for various multi-component mixtures. With this, I would like to thank you for your attention, and please get back to me if you have any questions regarding running any of these simulations. Thank you.